What's up, math scholars and math haters? This is Mr. W. Today we're going to continue our study of probability, and this time we're going to look at something called combinations. Now, these are very similar to permutations, but there is one key difference. So here is the basic definition. A combination is when you pick out a certain number of items or people or anything you want to think of from a group. But the key difference between a permutation and a combination is that in a permutation, the order in which you pick people matters. In a combination, the order does not matter. So, for instance, in the permutations video, we started with an example of Olympic swimmers where in a race of 8 people we had to figure out how many different ways there were to give out the gold, silver, and bronze medals. But this time we're thinking about maybe a qualifier race or something where we would just look for the top 3, and it wouldn't matter who finished first, second, or third. So this is one way that we know this is a combination question, because the order in which these 3 people finish in the group that we're looking for does not matter. So the basic idea of a combination is that we're going to start by figuring out the number of permutations. And if you remember, that was basically we start our 8 factorial, but we only write the first 3 numbers. So we started 8 factorial, wrote the first 3 numbers of this. That's 8 times 7 times 6. But this time, since order doesn't matter, we have to do something else. We have to actually divide by whatever number of possible orders there were to pick out those 3 people. So essentially, we start with permutations, we divide by the orders because order doesn't matter, and those orders are just going to be the factorial of however many people we're picking. So 8 times 7 times 6 divided by 1 times 2 times 3. I'm going to go ahead and do a quick shortcut. This is a trick you can use if you ever have to do one of these without the benefit of a calculator. I can see that 6 is 2 times 3. So I'm actually going to go ahead and get rid of all of these. So I've gotten rid of a 6 on top. I've gotten rid of 2 times 3 on the bottom. This leaves me with just 8 times 7, which is 56, divided by 1, which I actually don't need to write now. So that means that there are 56 possible groups of 3 racers who could advance to the next round, as opposed to in the permutations problem, where there were 336 ways to pick out a gold, silver, and bronze medalist. So next example, this will also probably look familiar if you remember the permutations video. We're trying to figure out how many ways are there to give 4 of the same prize to 12 people who entered a raffle. So this time the prizes are all the same. There's no first prize, second prize, third prize, and fourth prize. Therefore, the order in which we give out these prizes doesn't matter, and we know this is a combination question. So I'll go ahead and start this. Thinking about this to start with as a permutation. This is 12, 12 pick 4, which means I'm going to start my 12 factorial, but only write the first 4 numbers. So that's 12 times 11 times 10 times 9. But once again, I need to divide by the number of orders that we could have picked out those 4 people in, because this is a problem where order doesn't matter. And once again, I'm going to go ahead and look for some shortcuts. I'm going to start by seeing that 12 equals 4 times 3. And I'm going to say, okay, since 4 times 3 equals 12, I can just get rid of all of these. And now I have this 2. I don't see a 2 up here, but I do see an even number. And I'm going to say, okay, instead of 10, I'm going to call this 2 times 5. Which means I can get rid of 2 in the numerator and 2 in the denominator. Those cancel. So essentially, I leave myself with 11 times 5 times 9, which is 495. There's 495 ways to just give 4 of the same prize to 12 people who entered a raffle, as opposed to the permutations problem that looked very similar to this, where the answer was, I think, 11 or 12,000, something like that. So I think we can already see that thinking about permutations versus combinations, your numbers can get a lot smaller. And I think we're starting to see a little bit of a pattern here. So I actually want to go ahead, bring up that first board where I had the definition, and think about what the formula for this is. All right, so here's the definition again. Now, the formula for combinations is very similar to the formula for permutations. Just like we started our combinations problems by thinking about, okay, what are the permutations, and let's get rid of the orders. So the permutations formula, except this time it's NCR for combinations, we're going to start with n factorial in the numerator, and then n minus r factorial in the denominator. This would get us to like the 8 times 7 times 6, or the 12 times 11 times 10 times 9 from those other two problems. But if you remember, we needed to divide by the number of orders in which we could pick these r people in the first place. And this is going to be the last little bit that I will add to the permutations formula to get the combinations formula. Because in the denominator of this fraction, we're also going to take the factorial of just the number of things that we need to pick. So now I'm going to bring up my next board with some examples, and the key point of this is going to be to go over the symmetry of these combinations. All right, now that I've given the formula, I'll go ahead and find these with my calculator. I'll just go ahead and find this top row of numbers. To use the combination formula in the calculator, just like permutations and factorials, I'm going to press Math, go left to the probability menu, and I see NCR here. Now, if you remember with permutations, we had to type in a number first. We had to type the number of things that we were picking from, and I need to do the same thing here. So this will be 6, Math, probability, NCR, 0, and that's just 1. If you think about it, this is basically asking how many ways are there to have 6 things and not pick any, and there's just one way, you just leave them all there. So 6 choose 0 ended up equaling 1. Now for 6 choose 1, I'll type it in the same way. 6 choose 1 ends up being 6, which does make some sense, because if we think about we have 6 things, how many ways are there to choose just one of them? Well, that's the same thing as the number of items. 6 choose 2. Whoops. That's 15. 6 choose 3 is 20. 6 choose 4 is 15 again. Okay, so it looks like these are starting to get smaller. Let me go ahead and write all this down as we have it. And finally, 6 choose 5 equals 6, and 6 choose 6 is just 1. So if you remember how I said that combinations are symmetrical, we can kind of see that with 6 choose every possible number for that from 0 all the way up to 6. But now I want to get to why I have Pascal's triangle here. If you remember Pascal's triangle, then you remember that we get whatever number's here by just adding the two numbers that are above it. So 1 plus 4 gave us 5, 4 plus 6 gave us 10, and so on. If we keep this going, though, I'll make my 1s along the edge. 1 plus 5 is 6, and there's a 6 over here. 5 plus 10 is 15, 10 plus 5 is 15, 10 plus 10 is 20. And you might already be starting to see these numbers exactly match these numbers, every single one of them. This is one reason that Pascal's triangle is as loved as it is by math people, and it's one reason that I dedicated an entire video to it, because it leads directly into this idea of combinations. You don't actually have to have your calculator if you can just do some quick addition, do a couple quick rows of Pascal's triangle, and then say, okay, this is 6 choose 0, 1, 2, 3, 4, 5, 6. And just to highlight how the symmetry works specifically regarding the formula, I want to go ahead and just do this last example. How many ways are there to choose 5 students out of a class of 40 to present projects? Now this is, of course, different from the other permutations example where we were looking for the top 5 GPAs, so we could see who was first, second, third, fourth, and fifth. So I will actually go ahead and write out the formula here to start with. This is going to be 40 choose 5. So to start with, this is my n, this is my number of things that I'm choosing from. So my formula is going to need to start with 40 factorial, which I'm not going to figure out. I will absolutely not figure that out because that is probably going to break my calculator and my brain. Down here, we have, we start with the subtraction thing in the parentheses. 40 minus 5 all factorial, and then we just need, for the last bit that was not in our permutations, the 5 factorial. So this would end up being 40 factorial over 35 factorial times 5 factorial. And I won't solve this yet, because I want to do the same thing with asking about 35 students. This would be 40 choose 35, and this would be equal to, once again, I start my formula with the factorial of the number of things I'm choosing from, come down here, and do my subtraction factorial, and then my factorial of just this number of things that I'm picking. And now if I evaluate this in parentheses and write this out, we have 40 factorial in the numerator, 5 factorial times 35 factorial in the denominator. Now I chose these numbers intentionally in order to show that we have 40 factorial, 35 factorial, and 5 factorial in both of these expressions. And I'm actually going to go ahead and do both of these in my calculator so that we can see that they all come out to be, or they both come out to equal the same number. So this would be 40 choose 5, which ended up being 658,008. And down here for 40 choose 35, once again, 658,008. And the key idea of this whole board, the second part of working with combinations, was to highlight the fact that these are symmetrical. And if we think about it, choosing 5 students to present a project is the same thing as choosing 35 students to not present a project. And that's why there's the same number of ways to do both. In fact, we can even match a group of 5 students with another group of 35 students. If we picked 5, we left 35. If we picked 35, we left 5, and so on. So I hope that's helpful in whatever studies that you're doing for this idea, and good luck with whatever work or assignment you have to do for this.